Hello, everyone. Good afternoon. Welcome to our talk on Cognitive Memory Manager, or CMM for short. CMM is a persistent reasoning memory system for AI coding assistant. My name is Amit Arora. I am a principal solutions architect at AWS and an adjunct professor at Georgetown. I'm joined here with Sazan.
My name is Sazan Khalid. I am a first-year master's student at Georgetown's Data Science and Analytics program with a specialization in AI. I'm also a part-time data scientist at the Massive Data Institute.
With that, let's get started. Okay. So I'd like to start with a short anecdote of how CMM came about to be. So about a year or so ago, or just about a year ago, I started building this open source project called the MCP Gateway Registry Project. Now that project started gaining a lot of traction, both within AWS and outside. So I was wanting to share that with people within the organization, and there were people on the internet contributing PRs and so on and so forth. So what then happened was that I obviously wanted to share things like, hey, here are coding stylistic guidelines. But I wanted to share something more. As people started contributing pull requests to that, I thought that I wanted to share something that could be called the theory of the program, something that could inform why were certain architectural decisions taken the way they were taken, why were certain design approaches brought about. And I thought this is the theory piece of it is we are in the day of AI where there are new models coming out every day. But if I were to rewind, like, I don't know, 30, 40 years, the great Peter Knorr had a paper in 1985. It was called Programming as a Theory Building Activity. So I wanted to share the theory of that program so that people would get to the same architectural decisions with which I had designed that particular solution, rather than in addition to solving the bugs or contributing new features and so on and so forth. And then I thought, well, how could I do that? I mean, there were things like markdown file written in documentation. There was the Claude.mde or agent.md file. But I needed something more than that. And I was like, where is this theory available today? And then it occurred to me, actually, all of that theory was available in this very rich conversation that I had with the coding assistant. So I was using Claude Code. So all this multi-turn conversation with the coding assistant where given a particular bug, it would say, oh, I would decide to fix it this way. And I would think, oh, no, maybe this is a good solution. Either go ahead or do it this other way. Or certain architectural decision. I want to design a new feature, but here are three options. Which one do I select? So that back and forth communication with that coding assistant, that actually contained a goldmine of context. If there was a way that I could extract this theory from that multi-turn conversation, from this tons and tons of sessions with that coding assistant, that would be incredibly powerful. And then once that theory was extracted, I could share that as a memory bank with other developers so that they are not starting from scratch. They start from the point where that theory, the tips and tricks, the best practices, the coding guidelines, things that would not fit into the regular agentic AI assistant markdown files would find a home. That is where CMM came about. And the idea that the debugging time was reduced was obviously a good thing. But my perspective in building this thing was to share the theory of that program. So with that, we talk about what is CMM. So CMM is an open source solution. It is a system that is session agnostic. I could take advantage of these insights across multiple coding sessions. It is model agnostic. So today we have Anthropic releasing Opus 4.7, but when I started coding this, feels like a long time ago, but it was probably with Claude Opus 3.7, right? So we wanted this memory system to work across sessions, across models, even across coding assistants. So within AWS, several developers would use Kiro. There were people who, outside of AWS, contributing PRs to this, were using Codex. So how could we have a system that was session agnostic, model agnostic, AI coding assistant agnostic? Okay. So the way CMM, Cognitive Memory Manager, is able to do all of that is in a three-step process: capture, consolidate, and share. So these rich multi-turn conversations, these JSON-L files in which the interactions between the user and the coding assistant exist. So at the first step, we take those raw conversation at the end of a session through a hook or through a user-initiated command, and then say, well, this raw conversation is useful, but what is really useful is certain important pivotal points in this conversation. Here was an investigation. This was a pivot point where the debugging approach changed. This was a hypothesis. This was a aha moment. So we want to extract that. So once we extract that, which is as part of the capture step, we could share those, but then there was something even more powerful than that. These individual nodes, these hypotheses or summaries or discoveries, these are factoids. They are very useful. But there is something more useful. If we could consolidate these factoids, if we could consolidate these nodes and create higher level patterns that could be shared. Here, such as, here is a strategy for how to debug this type of problem within, this particular software solution. Now, as I was doing that, I realized, well, this is actually applicable not just to one repository that I was working on, but this is actually applicable across multiple repositories as well. So we would consolidate those nodes, those factoids, into higher level patterns, which could be investigation summaries, which could be strategies, which could be design ideas. And once that is done, and this is not a one-time activity, it keeps on happening as new sessions come in and out of existence, this memory bank keeps on getting updated. So once we have those higher level patterns, we would want to store them in some form of a data store. So we used a vector database, but that's a placeholder. It could be any data store which would end up supporting hybrid search. So both semantic search and lexical search, you could use one of your choice. We chose ChromaDB, but that choice is, that's just one choice. So the three-step process of capture, consolidate, and share. So once these details, these insights are there in the database, now another developer does not start from scratch. They start from that memory bank to begin with, right? Let's get into details.
So first, before I dive into anything, I just want to do a quick cap of what the current memory landscape is in terms of what existing functionalities exist. This is not very comprehensive, but I just wanted to start with it so we can pan out what is CMM contributing to this. First, we can divide it to like 4 parts. There are platform native initiatives for memory. So Cloud Code has auto memory and auto dream. This is when the agent can take notes about its build, about your developer references, and as well as some debugging insights. There's community structured mechanisms. So developers have been building these organized memory systems. These are called topic directories, so like tools or domain slash. And these are very helpful. They're scoped still to one developer. There are memory frameworks like Mem0 and Letta. These are purpose-built libraries for agent memory. They're built on knowledge graphs and vector storage. And there is also bigger infrastructure that you can think of as having memory capabilities. These are Claude-managed agents. They have memory listed as a research preview. Chroma Cloud has its own managed vector database that you can do a search over. Now, let's think about what is CMM, or a cognitive memory manager, adding to on top of all of this. First is reasoning extraction. Agents will stop making mistakes in the past, or they will just be making those mistakes, but the future sessions don't need to be facing those same mistakes again, because those past reasoning sessions are brought down to future sessions as well. So it's not just outcomes, but reasoning as well is being transferred. Second is cross-developer sharing. So a new developer on your team on this repo can start with the team's accumulated experience. The third is there's two-scope classification. So there is engineering decisions and knowledge and memory that can be specific to a specific project, but it could also be some general knowledge that is beneficial to the entire team. So there is that scope classification as well. Finally, there is automated extraction. You don't need manual documentation for this. This can run as a hook at the end of your session automatically. And yeah, so that's just a quick cap of what the current memory landscape is. Diving into the important part, and that is the architecture. How is the reasoning is being modeled, extracted, consolidated, stored, and delivered? The key way and the core data structure of CMM is what we call a reasoning DAG. It's a directed acyclical graph where each node is mapping those extracted reasoning patterns, those reasoning patterns that I will get into that we care about, and the edges quantify a causal relationship between those nodes. You can see on the slides that there are 6 types of nodes that our extraction layer looks for when it is going through these sessions. Let's go into each one of them. Starting with hypothesis. Hypothesis is just basically the agent forming a theory. These are the parts of it that says, maybe the issue is this, I suspect, or let me check whether, when your agent is going through these thought processes, the agent is reasoning what might be wrong before it has the evidence. Investigation. This is when the agent is gathering that evidence. It's going through your directory, it's reading files, it's running tests. Basically, this is the workhorse node type. You can expect that most of the sessions are investigation nodes. Then we have a discovery node. This is when you have an unexpected finding. The agent found something that it wasn't looking for. It found that X is true and not Y. This often will redirect the entire investigation for the agent. Then you have a pivot. This is the most important node. The pivot node is when the agent is explicitly changing its approach. Let me try a different approach. That didn't work. Instead, I'm going to do this. Pivot is what we call a high signal node. What does that mean? A signal means it has information value. So a high signal node is one that carries a lot of useful information for us relative to all the noise around it, all the noise in that session. Pivots are high signal because they mark that boundary for us between a failed strategy and a new one. Then we have dead ends. This is a failed approach. An error, a test failure, a command that is really returning nothing useful. What's particularly useful about dead end is when you pull it into your repository, your agent's not going to make that same mistake again because it saw it was a dead end in the previous session, so it won't repeat it. Then you have, go ahead. No, you go.
The one thing I'll quickly add to that over here is that at the bottom part of the slide, you see some sort of a pedantic model describing the schema of how these nodes are stored. And this is one of the more important part as to how we achieve agent agnostic behavior over here, or AI coding assistant agent agnostic behavior, because we map those JSON-L files or other formats into this normalized schema that you see over here. This can then be stored and retrieved from a vector database or through semantic or lexical search. And therefore, no matter what coding assistant you use, this would still be relevant, right? So there is the piece of data engineering is what lends itself to agent agnostic utility of this solution.
And then we have the solution node. This is your working resolution, the fix that actually worked. So in your transcript and in the extraction, if we see a dead end node and a solution node close to each other, that's a pretty important arc because that means that's when the problem started and that's when the problem ended. You can see on the basically on the code what the JSON is storing about these nodes. You have the node ID, and the node ID's parse that it tells you which window it came from in the extraction layer and which node of that window is. We'll go deeper into that in the next slide. The node, what node type it is, it's a dead end, and there's summary, and then there's evidence. The evidence is just basically what triggered this error, this dead end, and then also there's the confidence. Confidence is 0.88. What does that mean? That means how confident our extractor was in this classification as a dead node. And then finally, there's the message range as well. This covers exactly which exact range and lines from your JSON-L session transcripts it came from so that you can go directly back to it. So yeah, this applies to any project. As you can see, the scope is on team. When the scope is the team, that means this kind of error, which is bcrypt call error, can apply to everyone on the team. Anyone can face it regardless of project, most likely, and it's not specific to a specific repository, for example. And you can see what are these edges. The edges basically connect the nodes, as I said, causally. The dead end is followed by a pivot, then that edge is a triggered pivot edge. When a hypothesis is leading to an investigation, that is what we call an informed edge. The graph, is important to note, moves forward in time. So if the agent wants to go back to a previous solution or a previous tactic, that will result in a new node in the graph. There are no cycles. So why do we want to model it this way? Because the relationships between these reasoning moments are the real value that we see. A standalone dead-end node is just an outcome. It is just an error. A dead end that is connected to a pivot, that is connected to a solution, is a complete debugging narrative that a future agent can use. Now going into extraction. So we have these JSON-L files, as we said, and we're extracting them into these nodes. Then we have to be very particular about the reasoning trajectories and how we are extracting. We implemented 2 tiers. One is just efficient, it's fast, it's automatic, it's free. The second one is really our star, and that is the one that is intelligently using an LLM, and that was what we call the cold tier. The warm tier requires no LLM. It runs automatically at the session end. You just basically have to put into that stop hook to call a stop hook that is wired into your settings JSON file. So when you close the session, the hook fires, the transcript is parsed, and then 3 heuristic strategies are run in parallel. These are quick ones. There's keyword classification just for regex patterns. There's error resolution pairing. It tries to connect those dead end nodes and the solution nodes. There's explicit conclusion detection. So when you see your agent thinking, it will flag things like, I found that, or the issue was this. So when 2 strategies independently flag the same part of the transcript, the one with the higher confidence will get a corroboration boost. So the whole thing is under a second. It costs nothing. It's not very smart, though. Our star is the gold tier. The gold tier uses LLM for higher precision. It counts the tokens in each one of your messages using, we use the Anthropic SDK, and then packs them into windows, filling 45% of the model's context. We've learned that filling the model's context to the max actually undermines their performance, so 45% is the benchmark we used. It's around 85,000 tokens per window. So each LLM call will then return a list of about 12 classified nodes from that window. And adjacent windows will overlap by around 750 tokens. So if you have a reasoning trajectory that goes over the boundary, we're not cutting up that reasoning trajectory and not interrupting it. The key mechanism that really connects these two is the deduplicator. Basically, let's say your session ended, you automatically and quickly run the warm tier, you've built up that profile with the nodes. Then after, you give it the -- cold flag to run the LLM through it. The LLM is going to have its own classification of the nodes. The warm tier is going to have its own classification of the nodes. Basically, the deduplicator will match them on semantic similarity, and then the one with the higher confidence will be the one that we maintain in the final version of the cognitive profile. Now we can move forward. Now, what is, as Professor Arora talked about, is the session that we have these many nodes. We have about 400 nodes from a session, and they're all very substantial. But if you start a new session and I give Claude these 400 nodes, it's not very easy for it to just understand what's going on, which is why we start building these cognitive profiles. These are structured documents that the agent can actually hold on to and load. The first step of building a cognitive profile is the embedding. So every node summary that we just talked about gets embedded using OpenAI's embedding model. The embedding text is formatted like there is the summary, there is the dead end and what that dead end was. And this happens in a quick batch calls using the OpenAI API. The second step is to cluster. This is when we do agglomerative clustering over those embedding vectors using cosine distance with a threshold of 0.4. Why not use k-means or other ones? Is because we don't know how big or how many are in these clusters beforehand. And agglomerative clustering with distance threshold sort of handles the different numbers of natural groupings. Then the 0.4 threshold was tuned empirically. If you make it too tight, then you don't get that many. If you make it too broad, then you get too many nodes in the cluster. The minimum cluster size is 2, and it goes up from there. The third step is to classify. This is when the LLM comes in. So for each of those clusters, we send these clusters to Claude and we ask it, is this an architectural insight? Is this a pitfall? Or is this a diagnostic strategy? The LLM also in this step will assign that scope that we talked about. Is this a project level scope or is this a team level scope? So is it a general engineering pattern that can apply across projects or is it specific to this project? Fourth, we have the ranking. This is when those pitfalls we talked about get a special treatment. They are ranked by frequency. Basically, how many of those sessions that we parsed have this common error. That's going to be a pitfall with a high confidence. So a pitfall that was mentioned in 5 different sessions, an error that was faced in 5 different sessions, is rated high. That means it's more prominent than it should be. And then where the extraction found solution nodes near a dead end node in the original transcript, the resolution strategy to that path is also attached to the pitfall automatically. This is how basically our profile can say, this is a trap and how you can fix it.
So another thing from just taking up from that pitfall topic and things that happen repeatedly, some emergent behavior, if you will, that we didn't think of that would come from this sort of a design was, well, if we see these pitfalls with a super high confidence score, then we can create a downstream pipeline to create GitHub issues for those that these are actually bugs or some sort of poor design decisions that should be fixed. So this is not something that we don't want somebody to wait on those and flag them that, hey, if you encounter this particular situation, then we can very quickly fix this. While that is true, we can do one better by having a downstream analytics on these pitfalls themselves and create a work stream to say, go create GitHub issues, scan the memory bank for all the pitfalls with confidence, let's say, greater than 0.95, and go create GitHub issues, which can then fixed automatically so that this problem itself is alleviated. So that was not something that we thought we were looking for, but then when that pattern emerged, we said, okay, like that's really cool.
And then the fifth step is to write. This is when that assorted profile is persisted to ChromaDB using a serialized cognitive profile object. And it simultaneously will write a markdown file at a .cognitive directory in your repository that you're interested in. So this cognitive profile is cached into whatever repository you're working on, and that memory and those insights are all there ready for you. The markdown format matters because it's easiest for the LLM to read. So below are the 3 pipelines. It's just an example of what we're gonna show you soon as well, a full test through, is the real data from 43 ingested sessions from the MCP registry. There was an insight about how authentication is handled at the gateway layer. Individual MCP servers receive pre-validated requests. There was a high-level pitfall. There was another one of these, and then we're going to run through that in a test later. And then there was also an output for strategies. So basically, what strategy to use. So yeah.
By the way, we did end up fixing that pitfall. Once we recognized that, okay, that is happening, we need to fix that.
Yeah.
Okay.
Oh. There we go. Now to get into how do we store and how do we retrieve. Now that we've extracted those nodes and we've built that cognitive profile, we want to build a way that supports fast and relevant retrieval to your current repository. So this shows 3 stages to how those profiles and nodes are stored, how they are searched, and how they are delivered to your agent and to your repository. On the left, every reasoning node is stored this way. You can see it has a summary. It has the embedding vectors, 1536, and then the metadata associated to it. The project ID, which is the project that this node was relevant to, was extracted from, the node type, the confidence score, and then the scope, and the developer that extracted that node. This will be essential soon. You'll see why it's essential very soon. There are 2 storage modes. There is the local mode. So basically when you cache in and bring it in, that memory and that cache profile is locally stored on your computer. And then soon we'll talk about the shared memory system as well. In the shared mode, a ChromaDB instance is open alongside the local one. This is the one you share with your whole team. It has 2 parts to it. Just to rephrase also that our shared memory system is for Chroma Cloud, but then you can use other services as well. In shared mode, the store maintains 2 collections. There's a staging collection for nodes awaiting review. These are human review. And then there's that main collection for your team of all of the approved nodes. The local store is only locally available to you. It's the source of truth for you and your project. And that shared memory store can only be accessed and pushed into the same way you push and pull out of a GitHub. It's push, pull, review into that shared memory store. So what does this mean for you as a developer? Your local store is empty. You do a CMM pull and you fetch all the approved project nodes that are relevant to your repository and all of the approved team level nodes that could also be helpful to your directory. And then they are all stored in locally onto your computer as that cached profile. In the middle, we see how do we search. So semantic search will embeds the query into the same vector space and finds those nodes by cosine similarity. This is what lets us search for IAM routing surface. A node store gets a IAM manager factory function. I'm going to speed up a little, so we're short on time. The last node is we cover delivery. So how do we deliver this? As I said, there's the cached profile locally onto your computer. And then there are also CLI commands for you. Same way you would invoke a skill, just do So you could do /search, and you could put in a specific query, /diagnostic strategies, put in a diagnostic strategy that you want to try, and it will see if you've tried it before, /pitfalls you've faced in this repository before. I'm going to go through this quickly. How would you, as a developer, start getting this started on your computer? Again, this is just regular install methods that you can use. There is a configuration. Basically, you initialize the project, you clone the repo, then when you go into that repository of the project you want to start working on and retrieve relevant memory into, you want to run it the cmm init command.
So the GitHub repository that we'll share with you very shortly contains all of this, so we can...
Exactly.
Yeah.
Shall I just move forward then?
Yeah,
okay,
please.
Okay. And then there is that team mode that I just talked about briefly. I'm going to go through this really quickly. There is the share store. So basically, let's say you want to start accessing that shared store. You just run this command, cmm init. You put in the flag shared, so you're not just operating it locally, and the path to that shared memory store. And if you want to push in there, when you push your project and any new, let's say I got memory from the MCP registry into my project. I extracted new nodes, built new sessions. I push that new extracted nodes into the main memory session. There's a human in the loop approval. This helps from getting hallucinated nodes from confused sessions being in your main memory store, because anyone on the project can be retrieving bad or irrelevant nodes into your repository.
I think we'll quickly shift to an example.
Evaluation.
So we actually ran this. We created a data set of, once we started using this, we said, well, we need to create a data set of problems that this solution can fix. So how do we measure that, right? So we measured that by things like token efficiency, time to solution. Of course, we want the AI coding assistant to make less and less mistakes, which means it consumes less token, less cost. We also would want to measure time to fix the problem, super important, so developer productivity increases. And then we wanted to measure somewhat an amorphous thing called developer delight. Are people happy using this? Like, does our small team of 3 or 4 developers happy to use this thing because they can now resolve problems faster? So those are the kind of things that we measured. We'll move on. Well, one particular bug that we were looking on, and I'll not go into details over here, but point being that our solution supported this MCP gateway registry project, it supported multiple identity providers, and we added a support for a new identity provider, and it ran into a known problem. So the developers, just as a type of experiment, who were using CMM, next slide please, who were using CMM, they were able to resolve this with 61% fewer messages by looking at 71% fewer files. The total duration was much less, and then we ran a whole bunch of other simulation tests to figure out how true was that, right? So this was one situation that we created, and then we said, well, we should create some more, get some data, and see how effective that solution came to be. So these were the metrics for the project that we were working on, but we are trying to extend this and use this across more projects. Okay. Well, so here are you can scan these QR codes. This left one is on the CMM, and the right one is the MCP Gateway Registry project, which sort of started this whole journey. And if you found this talk useful, if you find these 2 projects useful, please add a GitHub star to our repositories. Thank you. So we are being told we have 1 minute for a question. If there's any question, we'll take one. And then we'll be outside, so we can take more. Okay, but I don't know. Let's pick the one closest, recency bias.
So this seems to be a continuously accumulating chunk of institutional knowledge.
Yeah.
How do you choose which ones go into the cache for the current session? You can't just include all of the knowledge forever because it will overflow.
That is true. So 2 parts to that, and we're still building this. So one is the human in the loop approval for what goes into the team cache. The second part is that we are adding some sort of a linter to this so that, old memories are aged out. Things like as bugs get fixed, these pitfalls or these other insights may not be relevant, or some design decision has changed. So we want to sanitize the stored memories that we have. So that's a linter that would run periodically, and that's how we are planning to address that. Okay. We will take more questions outside.
Outside, yeah.
Or we have time for one more. We have time for one more?
No, I think we'll just...
No. Okay.
Yeah.
We'll be outside. Thanks so much.